Hey, curious minds, have you ever wondered what makes all these tiny machines, everyday appliances, and complex gadgets actually work? What kind of science, engineering, or hidden systems are running just beneath the surface, behind the buttons, inside the circuits, beneath the shells? What makes your radio speak, your microwave heat, your phone browse, or your remote control respond with just a click? There's a world of mechanics and logic packed into every simple tool we use. Welcome to How Things Work, the channel where we uncover the secrets behind the systems that power your world. From the tiniest components to the big picture design, join me, Godwin, to break it all down clearly, visually, and piece by piece. But before we dive in, do me a quick favor. Hit that subscribe button and turn on the notification bell so you never miss another smart breakdown like this. All right, let's get started. Today, let's take a look at something you probably ignore until summer hits and your room feels like a microwave. Yep, the fan. Don't get too excited. Let's start from the beginning. You plug in your fan into a power outlet that sends electric current, usually around 110 to 240 volts, through the cord and into the control board. And when you press a speed button, 1, 2, or 3, you're telling the system how much voltage to send to the coil inside the motor. I will be making a video on how the switch works and how it affects the fan speed button 1. Just enough juice for a slow, quiet spin. Button 3. Full blast, like it's trying to blow the heat into next week. Behind that button press is a switch that activates specific windings in the motor. Think of them like gear levels. Now let's go deeper to the motor. Inside the fan motor is a stator, the fixed part, and a rotor, the part that spins, and on the motor is an oscillator unit and a capacitor. The stator has copper windings. When current flows through, it creates a magnetic field. But AC current alone won't make the rotor spin. That's where the capacitor comes in. This little guy stores and shifts electrical charge, sending power to a second winding slightly out of phase. That offset magnetic field, it gives the rotor a nice push to start spinning and keeps it going. Without the capacitor, your fan would just sit there buzzing, unsure of what to do, kind of like us before coffee. And then you have the oscillator unit. It makes the fan swing left and right. Inside, there's a small gearbox connected to the motor, converting rotation into side-to-side motion. If you don't want your fan to oscillate, you can usually turn it off with a switch or knob on top. Once the rotor spins, it turns the shaft connected to the fan blades. These blades are angled just right, like airplane wings, so when they spin, they push air forward in a continuous stream. But here's something cool. Fans don't make cold air. They move the air already in the room. That breeze helps sweat evaporate from your skin, and that's what makes you feel cooler. So how much power does a standing fan use? Typically around 40 to 75 watts, depending on the model and speed. Compare that to an air conditioner pulling 1,000 to 2,000 watts, and you start realizing how energy efficient this little dude actually is. It's basically the budget-friendly superhero of home cooling. Now, fans come in all shapes. Ceiling fans, table fans, tower fans, bladeless fan, exhaust fans. But the standing fan hits the sweet spot. It's portable, easy to move, has wide reach, and gives you speed control and oscillation. It's the Swiss Army knife of air movement. So next time your fan's doing its thing, know there's a tiny motor, a clever capacitor, an oscillating unit that's some smart engineering, making it all work. All you did? Press a button. If you found this breakdown interesting, give it a like, drop a comment, and hit that subscribe button for more behind-the-scenes breakdowns of the world around you.